The observations we've just described, along with our understanding of the physics of stars and gases, allows us to determine several important processes that shape galaxies as they form and evolve. These processes include gravitational collapse, which we've already seen plays a big role in star formation, rotation, which can be important for determining what kind of galaxy forms, star formation, which can happen just when the galaxy forms or throughout its history, and collisions between galaxies, which can drastically change a galaxy's shape, motion, and star formation rate. In the next few slides, we'll look at each of these in more detail. When we looked at star formation, we saw that stars form from dense cloud cores in the interstellar medium. When the mass and density of these cores get high enough, they can start to collapse under their own gravitational pull. Galaxies appear to start the same way, collapsing from clouds in the intergalactic medium, like the clouds we observe in the Lyman Alpha forest. The collapsing cloud turns into a proto-galaxy, the precursor to a galaxy. The clouds galaxies form from are billions of times larger than the ones stars form from, but they're also a lot lower density. The larger size means they don't have to be as dense. Nonetheless, we don't see any galaxy-sized clouds collapsing like this nearby. It's likely that in the early universe clouds would have been much more common, since the universe itself was more compact, so the average density of the intergalactic medium was higher.
When we discussed star formation, we mentioned that the spin of a cloud core accelerates as it collapses. The same will be true for forming galaxies. The rotation of the gas will speed up as the cloud contracts. If enough gas is going fast enough, then it will create a disk and hence a spiral galaxy. On the other hand, if the cloud has very little spin, then almost all of the gas will contract towards the center, and an elliptical galaxy is likely to form. However, it's also possible that collisions can change a galaxy's spin. A single off-center collision can make a galaxy spin fast, while many collisions from random directions will tend to cancel each other out and reduce a galaxy's spin rate.
As a protogalactic cloud contracts in on itself, its density goes up. Eventually, small clumps within the cloud get dense enough that they collapse to form stars. In galaxies where the gas had very little spin, all of the stars form from gas collapsing towards the center of the larger cloud. This would produce an elliptical-shaped galaxy, with all of the star formation occurring very early, since all of the gas is used up right away. Also, these stars would move in very elongated orbits rather than circles, just like the stars in elliptical galaxies, as well as the bulges and halos of spirals. In galaxies with more spin, the gas that formed into a disk doesn't get as dense because it's supported by the overall rotation. This means that some of the gas is prevented from turning into stars right away, and star formation can continue for many billions of years after the galaxy forms. This is what we currently see in spiral galaxies. The gas that went into the very first stars that formed would have had effectively no metals, nothing heavier than helium. We call these stars population 3, since they have even less metal than the population 2 stars we see in our galaxy. When such stars form, the upper mass limits we saw for ordinary stars no longer apply. They can form with sizes of many hundreds or possibly even 1,000 solar masses. Such large stars would use up their fuel and die very quickly, providing the metals that we now see in the next generation population 2 stars. A typical star in the disk of the Milky Way is tens of millions of times its own diameter smaller than the distance to the next star. So there's very little chance that any two random stars will collide. On the other hand, a typical galaxy is only a few diameters smaller than the distance to the next galaxy. So collisions between galaxies are very common in the universe around us. You can see in this group of galaxies several that are effectively touching each other. In the early universe, collisions were even more common. Space was more compact because it hadn't expanded as much as it has now, so collisions have been important throughout the history of most galaxies.
When galaxies collide, the stars don't actually hit each other. As we just saw, they're too far apart compared to their own size to have much chance of colliding. So the two galaxies seem to pass right through each other. However, while the stars don't collide, they do feel the gravity of the other galaxy as it moves through their own. This shifting gravitational pull distorts the shapes of both galaxies, especially if they're close to the same size, producing weird shapes with long tails flung out into space.
Galaxies may be moving towards each other at hundreds of kilometers per second, but the tremendous distances involved mean that galaxy collisions are incredibly slow. They typically take 100 million to a billion years to occur, so we only see a snapshot of a collision in progress. However, when we simulate the physics of galaxy collisions in a computer, it becomes obvious that we should think of a galaxy as being like a fluid, something that flows through space and bends and distorts because of the gravity of its neighbors. The links here lead to a couple of videos that show simulations of galaxy collisions. When two galaxies collide, there are several possible outcomes. If the two just graze past each other, then one galaxy can strip stars and gas off of the other, possibly giving a long bridge of stars between the two. As this small galaxy pulls past the larger spiral, it's stretching one of the spiral arms towards it. Two galaxies can also merge together. When two galaxies of similar size merge, the odds are they will form into an elliptical, even if they both started out as spirals. The pull of each galaxy on the other stars tends to randomize the orbits of these stars. This completely disrupts the disk and leaves a more elliptical shape. In our own local group, the Milky Way and M31 are moving towards each other, and it's likely that they'll collide like this in a few billion years. Before the Sun turns into a red giant, it may find itself in a very different looking galaxy.
Finally, large galaxies can simply swallow smaller ones in a process known as galactic cannibalism. We've already seen some examples of this when we looked at the star streams that are found around several galaxies, including the Milky Way. Also, the multiple galactic cores in the center of some giant elliptical galaxies are evidence of previous galactic meals.
We just saw that when galaxies collide, the stars don't hit each other. However, the gas clouds that make up the interstellar medium in each galaxy do collide, and this can have dramatic effects. When the gas clouds hit, the collision sets up shock waves in the gas that compresses it rapidly. As the clouds get denser, star formation occurs at a much faster rate than before. On the right, you can see the red ionization nebula being lit up by new stars as two galaxies crash into each other. In a typical spiral galaxy, the rate of star formation can go up 1,000 times over the normal rate. We call this a starburst galaxy. If a smaller galaxy goes to the center of a large spiral, the burst of star formation can spread out from the center in a wave, leaving behind a ring of hot, bright stars that becomes much brighter than the rest of the disk. You can see that here, and if you look carefully, you can see another of these ring galaxies by looking through the one in the foreground.
One of the most obvious characteristics of starburst galaxies is that they're very bright in the infrared part of the spectrum. That's because of all the new stars heating up dust in the star-forming regions. If you compare the different wavelengths on the right in this picture of the Cartwheel galaxy, you can see that the entire galaxy is glowing brightly in the infrared. Also, in this image of the Cigar galaxy, the bright jets of gas emerging from the center are the result of numerous supernova explosions in this galaxy, fueled by the starburst it's going through at the moment.
Lenticular galaxies may be the end result of the starburst process in a spiral galaxy. Remember that lenticular galaxies have a disk with little or no gas and no current star formation. That's what we would expect if most of the gas was used up in a starburst event.
Review the material we've just covered to help you fill in this table on galaxy evolution processes. You may also want to look back at the stellar evolution chapter, especially star formation, to remind yourself of which of these happen on a smaller scale when stars form. Notice that the answers may be different depending on the type of galaxy, so you should make a note of that in the table.
Let's summarize the major processes that affect the evolution of galaxies. There are 4 important processes: gravitational collapse of the protogalactic cloud, rotation of that cloud, star formation within the galaxy, and finally collisions between galaxies. The process of collapse mainly took place early in the history of the universe. We don't see galaxies forming today. The rate of spin determines whether or not a disk forms, and whether or not all of the gas is used up in making stars right away, or saved for a longer process of star formation over many billions of years. This determines whether a galaxy forms as an elliptical or a spiral galaxy, though later collisions can change this. Star formation and collisions happen much more in the early universe, but star formation is still going on today in spiral galaxies and many irregular galaxies, and all galaxies are still subject to collisions. Lastly, these processes are not independent of each other. For example, the collapse and collision processes can strongly affect both the spin and star formation rates.